So I want to give you some vocabulary to move us on from this point. When I say the word molar, I'm talking about for 1 mole of the substance. And when I say heat of fusion, I'm talking about the energy of melting. So heat of fusion is melting. And so molar heat of fusion means the energy needed to melt 1 mole of the substance. Likewise, heat of solidification is the amount of energy it needs to freeze 1 mole of the substance. So molar heat of fusion is symbolized as delta H of fusion is equal to the heat absorbed to melt 1 mole of the substance, and for water this heat of fusion is 6.01 kilojoules per mole. So if I am going from 0 degrees Celsius ice to 0 degrees Celsius water, I want to know how much energy it takes to change the ice into the water. And let's say I have 18 grams of water. I know that 1 mole of H2O weighs 18 grams, so I only have 1 mole of H2O. So if I have 18 grams of water, I only have 1 mole of H2O, and so the amount of heat I need to add to change 18 grams of ice at 0 degrees Celsius to water at 0 degrees Celsius, I will use this formula right here and see the amount of energy to change 1 mole of H2O, 1 mole of ice to 1 mole of water at 0 degrees Celsius. I'm going to multiply this by 6.01 kilojoules per mole, and that gets me 6.01 kilojoule, because the moles cancel out. That's a 6. That makes it worse. 6.01 kilojoules of energy that I need to add to the 0 degrees Celsius ice to change it into a 0 degrees Celsius water. Heat of solidification is the amount of heat lost to freeze the 1 mole of the substance. Remember that the for me to go from 0 degrees Celsius water to 0 degrees Celsius ice, I need to lose some energy, and that amount of energy that I need to lose is 6.01 kilojoules for every mole of water. So let's say I have 32 grams of H2O. I know that 18 grams is the weight of 1 mole of H2O, and that gets me 2 moles of H2O. So if I know that I have 2 moles of H2O, I could say, well, the amount of heat lost by 2 moles of H2O, I need to multiply that number by the heat of solidification, and that is negative 6.01 kilojoules. 6.01 kilojoules is the amount of energy that is lost by 1 mole of the water. Multiply that together, and now I have negative 12.02 kilojoules that I need to, or the 0 degrees Celsius water needs to lose in order to become 0 degrees Celsius ice. So this delta H of fusion, the heat of fusion, is equal to the negative of heat of solidification. They're just the same amount of energy, except that they're opposite signs of each other, because when freezing you are losing energy, and when melting you are gaining energy. Same amount of energy, just different signs. You may heat of fusion and heat of vaporization, heat of fusion and heat of solidification can be a value per mass, and if you have this heat of fusion or heat of solidification in maybe kilojoules per gram or kilojoules per kilogram, kilogram, you're just going to have to multiply these values by the mass in order to get the energy in joules. Okay, so you might want to watch out in the future, maybe in college or AP chemistry, if they give you this heat of fusion by kilograms or per mass, just multiply by the mass. Make sure you just end up with joules, which is the energy that you want. Molar heat of vaporization is the amount of heat or energy necessary to vaporize 1 mole of a given liquid. So in this case, for water, I am going from 0 degrees Celsius water to 0 degrees Celsius steam. And the amount of energy for every 1 mole to evaporate is positive 40.7, there's a typo here, kilojoules per mole. So it's heat of vaporization is 40.7 kilojoules per mole, not joules per mole. And in order to find the amount of energy required, I just have to multiply by the number of moles of the substance that I have in order to get the total amount of energy that is required for that vaporization. Please remember that during these phase changes, there is no temperature change. I'm going from 0 degrees Celsius ice to 0 degrees Celsius water, or 100 degrees Celsius water to 100 degrees Celsius steam. Opposite of vaporization is condensation, and so the molar heat of condensation is the amount of heat released when 1 mole of the vapor condenses into a liquid. Once again, I am going from 100 degrees Celsius steam to 100 degrees Celsius water. And the heat of vaporization is negative 40.7 kilojoules per mole. There's a typo there. Please see that typo right here. It's not joules, it's kilojoules per mole. Heat of vaporization is equal to the negative heat of condensation. Okay, so let's take a look at this this heat curve once again. Remember that in leg A, we're talking about ice. It's a solid substance, and in here for water, it's ice. The solid ice is raising its temperature from 20 degrees Celsius to 0 degrees Celsius, but it remains ice the entire time. And so in order to find out how much energy is needed or absorbed in this process, I have to change the number, I have to calculate that by C times by mass. This is not mole, this is mass. Q is equal to mass times by delta T times by C to calculate how much energy was absorbed in this process of heating up ice from a very cold ice to a warmer ice. And please remember that according to this chart, solid ice has a specific heat of 2.06 joules per gram Celsius, and so you are going to, in order to find out how much energy was absorbed in this process, you are going to multiply the mass of the ice times by the temperature change of the ice times by 2.06 joules for every gram of the ice to change its temperature by 1 degree, the specific heat of the ice, and so you're going to get energy absorbed in that way. Okay. Going to leg B, I am going from solid ice to, and it is melting, and the temperature is not changing, it is remaining at 0 degrees Celsius. It is a flat line, and so there is no temperature change. In order to find out how much energy was absorbed in this process, you are going to multiply the number of moles of the water you have times by the heat of fusion of the water. And remember that the heat of fusion of water is equal to 6.01 kilojoules for every mole of the water. This like C, remember that this is entirely liquid, and this liquid is raising its temperature from 0 degrees Celsius to 100 degrees Celsius, and the amount of energy is calculated by multiplying the mass times by the temperature change times by the specific heat of the water, and for water it's 4.18 joules per gram Celsius. This leg D, the liquid is turning into gas. There's a phase change once again. The temperature does not change. It remains at 100 degrees Celsius. No temperature change. In order to find out how much heat was required in this process, you are going to multiply the number of moles of the water that is turning into steam times by the heat of vaporization, and in this case the heat of vaporization for water is 4.07 kilojoules per every mole of the water. Here's my leg E, and the gas temperature is rising again from 100 degrees Celsius to higher. In order to find out how much energy was absorbed in this process, you are going to multiply the mass of the steam times by the temperature change of the steam times by the specific heat capacity of the steam. And looking at this chart, the specific heat capacity of the gas is 1.87 joules per gram Celsius, and so the specific heat capacity of the gas here would be 1.87. I can't write a 7 here. Oh my goodness. It's 1.87 joules per every gram degree Celsius. Please note that you want to know these numbers. Some of these numbers you guys can find on your cruncher, so please take a look at your cruncher and look for these numbers, alright? Not all of them may be there, so for those that are not there, you just gotta have to memorize. Okay. Remember that the heat of vaporization and the heat of condensation is significantly larger than the heat of fusion or solidification. So remember that the heat of condensation, that was negative 40.7 kilojoules that was released for every 1 mole of the steam to condense into a liquid. And then you have heat of solidification, which is only negative 6.01 kilojoules per mole, which means that very little energy is released during this freezing process. And the question that I'd like to ask you guys is, why is steam so dangerous? Why is steam burns or burns from steams so dangerous? More dangerous than being burned with hot water. Okay, and so that's something to think about.